Welcome to this core maths lesson on the mean and standard deviation. And today we're going to cover an old idea, which is the mean that you covered in GCSE and prior to GCSE when you did work on averages. And we're going to introduce a new idea called the standard deviation. This might be a new idea, although it does feature in some other A-level subjects. And we're going to do a deep dive into where this idea comes from and how or what it can tell us about certain data sets. Before we get into what the standard deviation actually is, I've just given you a bit of problem solving to do just to get us warmed up. So I've taken some sales figures from McDonald's and KFC, and they're having some sort of argument about who's performed best during this particular working week. Now, it's up to you to think about this, look at the data, analyze the data, and come up with a conclusion that will suggest who has actually performed better during this week. So I'll let you think about that. Please pause the video, spend a bit of time, come up with some calculations, and see if you can draw a conclusion as to who has actually performed better. Okay, and let's have a look at the solutions. Now, for this question, we're asked which fast food chain performed better. Well, there's a variety of things we could do. We've got a data set of 5 data points per fast food chain here. The data points are given to us to the nearest 500,000. So obviously McDonald's didn't sell 3 chicken nuggets on Monday. It was 3 million to the nearest 500,000, which is quite considerable. And we've got similar figures for KFC. So because we've got more than one data point, we can't just do a direct comparison for each. We have 5, so we're going to have to use averages. We're going to have to find an overall figure that sums up how well they've done. So let's think about what type of averages we know that we can apply to this situation. Well, the first thing you might have thought about is maybe calculating the mean for each of these fast food chains. So if we look at McDonald's first of all, let's see if we can find out what the mean number of sales of chicken nuggets was for McDonald's. So I've given you a bit of space to do some calculations for this. So let's fill it in. So let's have a look at the mean. And you'll have to remember how to calculate the mean. So we take the sum of all the data points and divide by how many there are. So let's just add them up first. So I won't use the decimal points. So 3 added to 8 added to 1, add 5.5, add 2.5, and then we have to divide that by how many there are. Well, there's 5 days, so it's 5 data points. Okay, now you may want to do this on a calculator. There is a video that I've attached to Teams which explains how to download the calculator emulator, although you don't need a fancy calculator for this bit. Okay, so here we go. I'm just going to use my ClassWiz here. I'm just going to drag it over to this side. Okay, so if we add up all those numbers, so we have 3 plus 8 plus 1 plus 5.5, add 2.5. Okay, that gives us 20. All right. Just write that in here. Okay, 20 divided by 5 is, of course, 4. Okay, so the mean number of sales for McDonald's is 4. Now, that's in million, okay? So the mean is 4 million. Okay. Right, so we've got one average for McDonald's. Now, it might be a good idea. Let's compare the mean for McDonald's with the mean for KFC. So we'll move on to KFC now. And we'll calculate the mean for KFC. So I'll do that in green. Get rid of the calculator. So here we have KFC. Sorry, I just made a mistake there. Let's get rid of that. Done it again. Okay, so look at KFC. We're going to do the mean for KFC now. So the mean, again, add up all the data points. So it's going to be 3 add 2.5, add 9, add 2, add 3.5. Okay, now I won't use the calculator for that. I just wanted to show you that you can use the calculator if you wish. There's 5 data points again. Now, if you add up all those, the 2.5 and the 3.5, that gives us 6. Add that to 3, that's 9. Add another 9, that's 18. And then 2 gives me 20. Oh dear, right. So this is quite curious. We've got the same total, and I'm dividing it by the same number of data points. So this gives me a mean of 4. So I'm hoping you agree with this. We've got a mean of 4 million for KFC as well. So at the moment, it looks inconclusive. So the question is, what do we do next? Well, do we have any other averages we can look at? Well, yes, we do. We could look at the median for each of the middle value. Perhaps we could compare the median and decide which company was more successful. So let's do the median. Now, for the median, there's a couple of things we need to do here. Firstly, we need to put these numbers in order. So for McDonald's, so we're going to start at 1. The next highest number is 2.5, then 3, then 5.5, and then 8. Okay, and while we're at it, let's do the median for KFC as well on the other side. So put the numbers in order. So we have 2 for our lowest value, then 2.5. Okay, then we have 3, 3.5, and much larger at the value 9. Okay, now looks like we're going to have some problems here. If we cross off from each side in pairs, as you know how to do, so those can go. The first pair goes on each of those. Then we'll cross off the next pair. So I'll use a different color for that. So this pair goes in each of these. The number we're left with on its own in the middle is the median, isn't it? So let's have a look what the median is. It's 3 for McDonald's, or 3 million, remember, because it's rounded to the nearest 500,000, and 3 million for KFC. So we've got another problem. So we've got a median of 3 million for both fast food companies. Right. Is there anything else we can do? Well, we could, if we've got the same averages, maybe the thing that would determine one from the other would be how consistent they are. So perhaps McDonald's is more consistent than KFC, and or vice versa. And what I mean is that their number of sales is more grouped together. So it's easier to predict how well their sales are going to go week by week or day by day. Okay. Now, this is a consistency issue. Arguably, the more consistent a company is, the better it is. Okay. So how could we measure the consistency? Well, we need to measure the spread of the numbers, and for that we need to use the range. So we'll have a look at the range now. So let's see how spread out the numbers are. So the range, now how do we find the range? Well, we need to look at the table and take the biggest number and then subtract the smallest number from it. Well, the biggest number for McDonald's was 8, which is there, and the smallest number is of course 1, which is next to it. Okay, so if you do 8 subtract 1, that gives us a range of 7. So in other words, McDonald's is sales figures. Sorry, beg your pardon, that's jumped ahead of myself there. 8 subtract 1, which is 7. So McDonald's sales figures are spread over 7 million, 7 million sales figures, essentially. So between 1 million and 8 million. So it's got a spread of 7 million. Hope that makes sense. Get a bit tongue-tied there. So that's that. So the range is 7 million. So we'll just write that in. Okay, we don't know how consistent that is. Let's have a look at the range for KFC. Well, we take the biggest number for KFC, which is, of course, 9. Okay. And the smallest number, which is 2. Okay, right. So if we do 9 subtract 2, again, we get 7. So again, like how are we going to distinguish which company has performed better? There must be a way. They haven't performed identically. We can tell that from the numbers. So we need perhaps a better method. Okay. In the meantime, I hope you agree with those figures. If you did the range, or sorry, I beg your pardon, if you did the mean but didn't do the median or the range, perhaps just add those in. And we just need to write a conclusion now, don't we? So the conclusion is simply inconclusive. We don't actually know which company has done better based on this information. We need something else. All right, so we need to advance and come up with something that's going to actually help us work out which of these companies did get the best sales figures. Okay, the pressure's on. We need to answer the question. Now, the range was no good. That means the spread of the data was identical if we take the largest values and the smallest values in each case, and both means and medians were the same. The mode was redundant. There was no case where we had more than one of the same number for each data set. So we need to come up with something else. Now, the numbers were different in each data set. Okay, so there must be some way where we can work out which company has done better. Okay, because the numbers were different. Now, before we do that, I'm just going to introduce a bit of notation for you. So we're going to look at McDonald's first as our first sort of case study. And we're going to talk about something called a data set. Okay, the data set X in this case. Now, when we're talking about a set in maths, a set is a collection of objects. Most usually it's numbers, okay, a collection of numbers. And we use a capital letter to denote the name of the set. So this is the data set here. And then when we write the data set, we put them in brackets and we just list all the data points in the set separated by commas. Okay, so in an abstract way, we can call the data sets X1, X2, X3, X4, and X5, meaning that there's 5 points in the set. Okay, and in the case of McDonald's, we know what those numbers are. Okay, we've got 3, 8, 1, 5.5, and 2.5. But I've just put them in set notation, as it's called. Another way to do it is to say, okay, well, we know from the way this is presented that X1 must be 3, X2 is 8, X3 is 1, and so on and so on. So we could put them in a table like this, and you can see that X1 corresponds to 3, X2 corresponds to 8, etc. All right, so that's a couple of, 3 different ways, if you like, of presenting data. Well, 2 in this situation. Now, what we could do is we could use the mean as perhaps some reference point. Okay, the mean is the average of the data. So if we use the mean as a reference point, perhaps we could examine each of the data points in a bit more detail. So the mean in this case, we've already worked it out, but we're going to call it something else. Now I'm going to give you a new name for the mean. It's called X bar. Okay, X with a bar over the top of it. Okay, this is notation for the mean. So rather than writing the mean equals 4 in this case, we can say X bar equals 4. And I'm going to write that down now. So for this example for McDonald's, we know that X bar equals 4. And that was 4 million, wasn't it? All right, now that's really important. We're going to have to come back to this. So let's put this in a box and make it look really, really important. I'm going to shade it in as well. So X bar is just a fancy way of saying the mean. Okay. Now, if the data points were all called Y1, Y2, Y3, the data set was called capital Y, then you would call the mean Y bar. All right, I hope that makes sense. So it's whatever letter you use for your set. Now, let's have a look at these data points and see if we can tease out some more information. We've got the mean, so I'm going to indicate the mean on this diagram on the right hand side. So I'm going to use a vertical line for this. So the mean's going to go straight down from top to bottom, and the value is 4. Okay, so we'll just label that as X bar. That's my mean, which is of course 4. And we're going to see how far away each data point is from the mean. So let's go back to our table and let's have a look at the first data point, which was X1 here. Well, X1 has a value of 3. So here's X1, okay, has a value of 3. So that's going to be there on this diagram. And let's just show how far away this is from the mean. So I'm going to just draw a horizontal line there. So we can see that 3 is 1 unit less than the mean. So I'm going to put a -1 in there. Now let's do the same for the other data points. And you could, if you like, pause the video and do this yourself and then just check that you agree once I've gone through the other 4 data points. All right, so let's continue. So if we look at X2 now, which is of course 8. So X2 on the left-hand column must correspond to 8 here. So it's going to live at that pair of coordinates there. So let's just see how far away that is from the mean. All right, okay. So we'll just count how many units away that is. So that's 4 units from the mean. The mean is 4. So we'll just make a note of that. Okay, so that's good. And let's have a look at X3 now. So X3 is 1. So if we put the line in, of course, that's going to be 3 below the mean. So we'll just write that in. That's 3 below, so -3. Okay, and we'll do the same for X4 and X5. Okay, so I've just skipped ahead. So I've added X4 and X5 to the diagram. Now, if we look at this, we can see that the distances do vary, okay, for each of these data points. And if we looked at the KFC data, you would probably see different distances because the data was different, although the mean was the same. So let's see if we can explore this idea a bit further and we can do something else with the information we've just found. All right, now, before we proceed with the rest of the idea, something that I didn't explain previously, which is a feature of the mean, is this symbol which we call sigma. Okay, it's a capital Greek letter. We use sigma in math, so it's featured here and here. Okay, and it's an instruction. In other words, it's an instruction to add up or sum. Okay, so if you see the word sigma anywhere, or the symbol sigma, it means to sum or to add up. Okay, so we have a new way of expressing the mean here. So we said the mean is X bar. Okay, this is the mean. And if you sum all your data points, so X1, X2, and so on, okay, that means we're going to be summing X, okay, more generally, summing the data set X, and we use the sigma to denote that. N is the number of data points. Okay, and it's just a nice way of representing what the mean actually is. So in the case of our set X that we wrote out earlier, if you want to find the mean of that set, you take all the data points here, so X1 up to X5, and divide them by 5. A shorthand way of doing that is to say, okay, because we're adding them up, the subscript, which is this I here, can be all the numbers 1 up to 5. Okay, so those numbers that feature at the bottom of the sigma and at the top of the sigma, those are called limits. Okay, and you might see them, the way it's formatted here is a little bit unclear. So another way you might see it is if you see the sigma like that, and then I equals 1 up to 5, and then the xi's. So it just means take all the xi's from I equals 1 up to and including I equals 5. And that's why we add x1, x2, x3, x4, and x5. So it's all those data points from I equals 1 up to I equals 5. Right, now we've done the graph for the distances of our data points from the mean. We can now look at these distances in a table. So we've seen the diagram, you can see visually what's going on. So we're just going to fill in the table and see if we can do anything with this. So for the sample data we had 3 was our x1. So for the column on the right hand side, which is this one, we have to take each data point and subtract the mean from it. That's what it's telling us, because it says xi, which is your data point here, and then subtract x bar. So let's do that. So, and I'll write the calculation out just so it's really clear. So we take the data point, which was 3, okay, and we subtract the mean x bar, which was 4, and we got -1. Okay, and what we've done there, if you want to just make it a bit more abstract, we've done x1 subtract x bar in that row. Okay, just remember, of course, I'll just write x bar again. X bar is equal to 4, and that's the mean. Okay, so we'll do the same thing for the other rows. So data point x2 was 8, and then we subtract the mean from that. Okay, and we got a distance of 4, okay, which corresponds to the diagram. Data point 3, we did 1 subtract 4, and we got -3. 5.5, subtract 4, and we got 1.5. And 2.5, subtract 4, and we got -1.5. All right, so those are all the differences between each data point and the mean. Right, what can we do with this? Well, let's have a look. All right, now, what we could do is we could take the average of these distances. Okay, if all the distances of the data points are different, what is the average distance from each data point to the mean? Perhaps we could do that. And that's what's represented by this notation here. Okay, so remember the sigma means sum. So add up. I'll just make a note of that. So add up. And we're going to add up all the xi subtract x bars. Okay, and we can do this calculation here. Once we've done that, we divide that by the total number of data points, which was of course 5, wasn't it? There was 5 data points. And let's see if we can take the average of those distances. So let's do it. So we've got space for the calculation. So we'll do sigma, and then each xi subtract the mean x bar and divide that by n. In this situation, well, the first difference that I remember seeing, which was x1 subtract x bar, that was -1, wasn't it, from the table? Okay. The second difference was x2 subtract x bar, which was 8 subtract x bar, or 8 subtract 4, which is of course 4. And then we had a difference of -3. This is all from the table on the previous on the previous page. And then we had a difference of 1.5, and then we had a difference of -1.5. And notice here, I've taken care when I'm adding negative numbers to put parentheses, put brackets around them. Okay, and we have 5 data points. All right, so let's calculate the average distance of each data point from the mean using this information. Now let's see what happens. So we've got -4 plus 1, beg your pardon, -1 plus 4, which is of course 3. Then I'm going to add a -3, which just cancels out. And then I've got 1.5, and then I've got a 1.5 to subtract. So it looks like I'm just going to get 0 over 5. So that means my average distance is 0. Now that can't be right. What's gone wrong? Clearly the average distance is not 0. If you look at that diagram we drew and maybe took the average length of those lines, you're not going to get 0, are you, for your average distance? Okay, if the average distance was 0, then everything would just be purely on the mean, wouldn't it? So something's gone wrong here. Those distances would not all sum to 0. Let's try it. Maybe it was something to do with the set of numbers. So let's try it again with a different set of numbers. I'm just going to scroll down here. So let's just scroll down the page and let's see if we can do something else with this. Okay, so for the next bit, I want you to sort of take over, and we seem to have got an average distance of 0, which clearly can't be right. Those lengths were not all averaging to 0. You can't have a negative sort of distance that you can measure. That just doesn't make sense. So we need to try some different data. Now, I've provided you with a table here. And what I would like you to do is just to make up your own set of data. Just choose six numbers, any 6 numbers you like. Okay. And just write your 6 numbers in the table here. It doesn't matter what you choose anything you want. For each of those 6 numbers, you're going to need to calculate the mean of those 6 numbers, and you're going to need to find the difference between the numbers you've chosen and the mean, and then write those numbers in this column here. Now, if the process was a bit too much to take in, on the right-hand side of the notes, I provided you with a recap of all the steps that we've just been through. Okay, so you can choose any 6 numbers you like, calculate the mean of those numbers, and then complete the third column by subtracting each data point. Said that the wrong way around, sorry. Subtracting the mean from each data point. Okay, so choose your own set of numbers. I'll choose my own in a second, and then we'll compare results. Right, so I've chosen a random selection of 6 numbers, nothing too complicated. I've calculated my Y bar. As you can see, I've just written the Y bar here, so we can see it for reference. I'm calling it Y bar, of course, because these data points have the script Y. Okay, so it's a capital Y for the data set. So each data point is Y with a subscript. And you can see over here on the right hand side on the ClassWiz, I've just put in this is my calculation for the mean. Just be aware on the emulator, it uses a comma instead of a decimal point, which can be a little bit confusing. But I've got my mean as 5.5. So my next task is I've got to work out the differences between each data point and the mean. Okay. So this number is crucial. So I'm going to be using this as reference. So let's take all these data points and subtract 5.5 from them. So we're going to have 3 subtract 5.5. Okay, we're going to have 1 subtract 5.5, 8 subtract 5.5, 5 subtract 5.5, 10 subtract 5.5, and lastly 6 subtract 5.5. All right, so I've just filled in those answers, and I think we're ready to calculate the sum of the differences between the mean and the data points. All right, so you've got a bit of space to do this on the right hand side. So we're going to calculate the sum, and we're going to do all the yi's. Nothing to do with being from Newcastle. Sorry about that. Minus y bars, and then divide by n. Now, n is, of course, 6 in this case, so just be careful. There are 6 data points, not 5 as in the previous example. So if I do that, what I've got to do is I've got to take my negative 2.5 and add the negative 4.5, add the 2.5. Okay, my calculator is going to get in the way, so just get rid of that and just erase a bit of this. Okay, and then add negative 0.5, make sure I get the signs on there, add 4.5, okay, and then add 0.5. Now, it's a little bit less obvious in this case because we've got some slightly more complicated looking numbers, but you'll see something interesting in a second. Divide all that by 6. Now, let's look at the numerators. Now, to add all this up, we can sort of compare and contrast, can't we? We've got some similar looking numbers here. So I've got negative 2.5 and I've got 2.5 there. They're going to cancel. Okay. I've also got negative 4.5 here and 4.5 here. They're going to cancel. And would you, Adam and believe it, I've got negative 0.5 and a positive 0.5. It all cancels out. Surely this is just a coincidence. Now, you can compare this with your result. You would have chosen, hopefully, some different numbers. Otherwise, it would have been an amazing coincidence. I got 0 again. The average distance is 0. Why is this happening? This is frustrating. We need to do something about this. Now, clearly, those distances on the graph were not 0. If you add up all those distances, you know, all those little lines that we drew, if we took them all, put them end to end, and then took the average distance, you would not get 0. Nowhere near it. Something's going wrong, and we need to do something about this method. And that's what we're going to do next. So now I'm going to propose an alternative method. We're going to call this method 1. So I've put the McDonald's data on there. Those are the differences that we took, so the differences from each data point in the mean. I've written those up, and we're going to look at something called the absolute value. Now, this could solve our problem, okay? Clearly, the reason why everything's cancelling out is because we have positive and negative numbers, and we're trying to add them together. And when we add them together, obviously there's cancellation. Now, in mathematics, when we use this word absolute here, it basically means, this is the very basic definition, we take the size of the number only, as in we take the distance of the number from the origin, or from 0, if you like. And more simply, what that means is if the number is negative, you simply just ignore the negative sign, okay, and pretend it's positive. So the absolute value of -1 is just 1. We just remove the negative sign. Okay, just going to make a note of that. So if you can get this down, that would be really good. So remove the negative sign. Okay, the absolute value of 4. Now, 4 is obviously, it's positive already, so that doesn't change. That's just going to be 4. Okay, the absolute value of -3 is 3. And absolute value of 1.5 is just 1.5. And we ignore the negative sign again. Now, the way we denote this is quite interesting. We use bars, okay? So if I wanted to say what is the absolute value of -1, for example, we put a bar around it. So I write -1 and I put 2 lines on either side. Perhaps I should just redo that just so we can see it a bit more clearly. So if I take the number -1 to find the absolute value, I will just stick 2 lines on the outside. That tells me that I'm finding the absolute value, so the answer is just going to be 1. So the way we could write this is in notation is quite nice. So what we could do is we could say, to find this magic number, this average distance from the mean, we could take the sum, and we could take all the xi minus x bars, okay, but we want the absolute values of them. Okay, so we're going to stick a bar around on each side. Okay, that means, so it's not a bracket, it's a bar, it's a straight line. That means it's the absolute value. And then if we take that number, we can remove the possibility that they're going to cancel out. And if we divide all that by how many data points we've got, surely that should give us a decent answer. So let's do this. So let's add up all of these numbers. So the ones that we've just discovered, or it's not cheating, by the way. So we're going to add up all these and then divide it by 5. Okay, so let's use the calculator for this. So we'll take 1. So 1, add 4, add 3, add 1.5, add another 1.5. Right, and we get a realistic looking number now. So we get 11. So this is equal to 11. And then we take the 11. Get the pen going. So it's 11, sorry. Divide that by 6. So we're going to get a decimal here. Oops, just having a bit of trouble with the buttons. Divide that by 6. So we get 11 over 6, obviously. So press the SD button. So it's about 1.83. So it's 3 significant figures. All right. So 1.83. Now that's a lot better. Now that seems a lot more realistic. Okay. So the average distance, according to this, for each data point from the mean is 1.83. Now that's a number that surely would not be the same for KFC. Okay, if we were comparing those data. Now, but there's more to it. We could actually use a different method. Now, the reason why this might not be advantageous is using the absolute value of a number is algebraically unsound. Okay, it's got problems. If you have large data sets, then finding the absolute value of each of those numbers and then summing them all can be tricky. So we need something that we could maybe manipulate better using algebra. So we don't have to simply go through all the data points and change their signs. And another way to do that, and I would like you to sort of tell me this, but obviously I can't at the moment, but have a think. Is there another way we can remove negative signs from numbers without just taking them away like this absolute value seems to do? Is there another way? Well, the answer is yes, there is. So we're just going to write up this sample data again. So this is method 2. Now what I've done is I've put the sample data back in. This is for McDonald's again, from the first data set that we saw right at the beginning, 381, 5.5, 2.5. And I've put the differences between each data point and the mean again. I've put those in. So the question is, can we get rid of these negative signs a different way? Well, the answer is yes, we can. And the way to remove negative signs is to square the numbers. Okay, I've got some watches there. Let's get rid of those first. So if we square the numbers, we're going to be taking the square of xi, subtract x bar. I'm going to square the whole thing. So in other words, we're going to square each of these, okay? Now that will certainly remove the negative sign, because if you multiply a negative by a negative, they become positive. So if we just square all these numbers and fill those in, we'll be ready to do the next bit. So I've just added the squares of each of those numbers into the final column. Now what we need to do now is, of course, we need to sum these squares. Okay, so I'll put a little space for the total here. If we sum them, so we're going to take the sum, so that's sigma. We're going to sum all the xi's, subtract x bars, squared. Okay, I hope that's clear. So taking the sum, just put the sum, it looks complicated, but it's just the sum of this column. Okay, so if you add up all those numbers, and we'll write the total in the bottom. That's 30.5. You can do that on your calculator as well. So this number at the bottom is 30.5. Now, if we just compare what we got previously in method 1, these numbers look a bit different. When we summed all the absolute values, we've got 11, and this time we've got 30.5. So a bit of a discrepancy here. If I divide 30 by 6 or 30.5 by 6, it's going to be around the 5 mark. So it's going to be very, very different. Well, let's identify the problem here. Let's just do it and see what may happen. So if I take the sum of all the xi subtract x bars that are squared and divide all that by the number of data points, okay, I'm going to be doing 30.5 divided by 5. So for this, let's get the calculator out. Let's move it out of the way. So I've got a bit of scroll on the page, but never mind. So if I do 30.5 and divide that by 5, I get 61 over 10, which in other words is 6.1. So what do we need to do here? So this is 6.1 exactly. Right. And that's not even, that doesn't even need to be rounded because obviously we're dividing 30.5 by 5. So there's a huge discrepancy between this value and this value. And remember, we're trying to measure the same thing here. We're trying to measure the average distance from each of the data points from the mean. So what's going wrong? Have a think about what could be going wrong. Well, the problem occurred when we squared the number. When we squared these numbers here, obviously squaring the number, you're making the numbers much bigger in most instances. If the number is not a decimal between 0 and 1 or 1 itself, I mean, if 4 becomes 16, minus 3 becomes 9, 1.5 becomes 2.25, the numbers are just becoming far too big. So we need some way of perhaps remedying that to undo the fact that we've squared everything. How do we undo squaring? Well, we take the square root. So why don't we take the square root of all this? So I'm going to take the square root, and this is where it looks really complicated. Subtract x bar squared over n, and all that is the square root of 30.5 divided by 5, just putting all the pieces together, which is the square root of 6.1. Now, again, we'll get our calculator out for this. We'll just switch that off. So the square root of 6.1, just come out of that. What do we get? Well, 2.45. So again, back out of there. So that's 2.45 to 3 significant figures, just fitting on the screen there. Now, there's not a massive amount of difference. Both of those numbers would round to 2. Okay. So we have a difference of opinion, but the end goal measures roughly the same thing. Now, what we've just calculated in method 2, this is what we call the standard deviation. Right? And I know what you're thinking. You're thinking, do we have to do this every single time we want to work out the standard deviation of a set of data? Well, of course, the answer is no. All right. This is just the bare bones. We've just constructed the standard deviation from basically a wish list. We wish to work out the average distance from the mean. We seem to have got that. Okay. The absolute value method is useful. It's there's a system called the least absolute deviations. Some science subjects such as astronomy would use that. It's arguably more accurate. There is a debate going on, but the standard deviation is standardized. That's why we call it the standard deviation. Okay, and it's widely used. It's friendly to algebra. Okay, and it gives you more or less the same result. So that's what we're going to use, and this measures the spread of the data. So it's a more accurate measurement of how spread out the data is, rather than using the range. So it's a measure of the spread of the data. Okay. So this was the standard deviation that we just worked out. Now, we looked at the range earlier. We didn't look at the interquartile range for KFC and McDonald's. If you'd done that, perhaps you would have found a difference in between the two companies. But standard deviation is more widely used. It's used across all kinds of statistical analysis across very a huge range of subjects, so not just maths. This is the formula for it, and we use the Greek letter sigma. If you want to write sigma, if you just draw an O and then just put a little tail on it like that, that will do. Sigma or sigma n, n being the size of the data set. Just some properties here as well. Obviously, the bigger the standard deviation, that means that the numbers are spread out more. And if it's smaller, it means that the numbers are close together. So that's that consistency argument. If the closer the numbers are together, the more consistent it is. And importantly as well, the units are always the same as those of the data. So remember, whatever you're measuring, when we do the standard deviation, we square the measurements and then we square root them at the end. So they keep the same units as the data. Another way of thinking about this, well, another piece of information that might be useful is knowing that the standard deviation is the square root of something called the variance. Okay. Now, there's nothing much more to say about that, really. It's just a case of the variance is just the standard deviation, but not square rooted. And I'll write it down for you here. So the variance, if I just put it here, we just denote that as sigma squared. Okay. Or sigma n squared, and you would just write it simply as sigma of all the x data, subtract the x bar data, all squared over n, without the square root. Notice as well, we've dropped this little subscript here where the x is. You don't necessarily need it. It's just telling you that's all the x data, all the pieces of data. You add them all up. Well, you add up the differences between those data and the mean, add them up, divide by n, and then take the square root of the answer. Okay, so I think it's time that you guys had a go at this. And we're going to look at the data for KFC, and we're going to calculate the standard deviation for those data for KFC next. Okay, so I'll give you a bit of time to do this. I would just pause the video and have a go at this this calculation. Just to give you a little bit of a start, I've put the KFC data here. I've called the data K. All right, if that's all right. That means that over in the table on the right hand side, the data points have the lowercase k in there as well. Now, and I've just written you a little step-by-step guide of how to calculate the standard deviation. All right, so just to recap what you need to do. Step 1, write out each data point in the second column on the table opposite. Okay, so just transfer the data from here. All right, just scribble across my page. I didn't want to do that. Just take all the data from here and just write it in the column over here. Calculate the mean of the data. Once you've completed the mean, then you can find out the differences between each data point and the mean. Then in the third column, you're going to square your results from the middle column. So you're going to square each of these numbers. Then step 5, you're going to take the sum of all those. Then step 6, just have to scroll down a little bit, just clear all that. Step 6, you're going to divide the sum by n. Okay, and I put a little asterisk next to that. That's the variance. Once you've got to that stage, you now have the variance. And the 7th step, square root your answer, and then you get the standard deviation. You don't necessarily need a ClassWiz to do this. Okay, you can do this on an ordinary calculator. Now, I would recommend using the table first while you get used to the idea. So if you write everything in the table and then pause the video, I'll go through the solution in a moment. All right, so I filled in most of the table. I hope you agree with those values. I'm just at the stage now where we're going to do the summation. So we're going to sum all those data points that are in the final column over on the right. So if you add all those up, you get a grand total of 32.5. Okay, so that's your sum of all your ki subtract k bar squareds. Now we can calculate the variance. So we're now up to step 6. So the variance, which we can call sigma squared, if you like. Okay, so that's going to be the sum. I'm just writing the formula out as well. All the k data, subtract k bar, all squared, divide it by n. Okay, so that's just the 32.5. And then divide that by 5. Okay, so we'll just grab the calculator for this bit. So we've got 32.5 divided by 5. And we get 13 over 2, in other words, 6.5. So this is going to equal 6.5. So that's the variance, okay? You can make a note of that if you want to. So this is the variance of k. That's the notation we use actually for that. Variance of k. Now, for the standard deviation, we now just take the square root of all this. So sigma is just going to equal the square root. You don't have to write it all out again, of 6.5. So you can use your calculator again for this. So I can just take the square root of the answer from the previous bit, which is going to be 2.55. Okay, and that's to 3 significant figures. All right, and that concludes the standard deviation for KFC. Okay, so for the last part of this, I've just written up the information we've just discovered from our calculations. So the mean we did right at the beginning, that was the issue because we had the same mean for both of them. We had the same range, the same median. Now we have the standard deviation. We can see that McDonald's standard deviation of 2.47 was slightly lower. So we need to write a conclusion here. We're going to compare the two sets of data. And before it was inconclusive, but now we can say that McDonald's, because it had a lower standard deviation, okay, lower standard deviation means it's more consistent, okay, on average. So that's what you're looking for. You're looking for a smaller standard deviation to show that the numbers were closer together, but only ever so slightly. So they were close together and the spread was only 2.47 million chicken nugget sales, which sounds a lot, but in the grand scheme of things, it isn't really. Okay, so just to summarize this, we haven't actually said what we think. We can say that McDonald's actually performed better. For that week. So we can't say anything about how they perform overall, but for that week, we have enough evidence to suggest that McDonald's did actually do better. Okay, so it turns out that the 5 days that we've just calculated are actually a sample from a larger population. What that means is a larger population of data. So what we need to do next is we need to calculate means and standard deviations of these larger data sets. Now, you're probably thinking this is going to be an arduous, onerous task that you don't particularly want to do. Well, this is where we bring in the ClassWiz. Okay. Now, if you don't have a ClassWiz, the emulator is available through Teams, and I've sent you, there's also a video explaining how to download the emulator. If you don't have access to that, simply just watch the video here, follow the instructions. And what I've done is I've put a step-by-step guide. There's 5 steps here, how to do it once you have a ClassWiz available. Okay, we'll figure out a way around the lack of ClassWizes just for now, but at least you've got the video and the notes as reference. So what we need to do is we need to take our data sets here for McDonald's and for KFC, and we need to calculate the means and standard deviation. Okay, so we have the step-by-step guide. So I'm just going to bring the calculator up now. We press the menu button, okay, for step 1, and move to option 6 using the arrow keys. Okay, so arrow keys, well, go down to option 6. There we have, that's the statistics section. We press equals and we're ready to go. So we're presented with a list of options. We're going to select option 1, which says variable. Okay, just press 1, and you'll be presented with an empty frequency table. Sometimes the frequency, there will be a frequency column on your table. Don't worry about that. If there is a frequency column, each data point is just worth 1. Okay, so just leave it fixed at 1. And then what we do is we just add the data set to this column. So if I just, let's have a look at the numbers. So we can just type in the numbers. That's no problem. So let's do that. So we'll start off with McDonald's first of all. So we'll have 3. We'll put that in. We've got 8. And we've got 1. 5.5, 2.5, we've got 8, we've got 7.5 there, we've got 10, we've got 9, we've got 5.5 again. Okay, I'm just going to move it over to the side for a bit. Okay, we've now got 7, we've got 8, we've got 1.5, and we've got 2. Okay, and it could continue, but we've got 14 data points there. It's a good idea just to check that we've got the right number of data points. So if we just count them, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it looks like I've inputted them without too much trouble. So now we've done that, we can check our instructions and see what we have to do next. So for step 4, step 3 was just talking about that frequency column, so don't worry about that. Step 4, we've entered all the data. We press the option key, OPTN, so I'm going to do that. And we've got another list of options. Now, at step 5, we're going to select option 3, which is the 1 variable calculation. So that's number 3. Okay, and we're presented with all this information. Now, this is what we have to understand how to interpret all this information here. So we're going to write up the bits that we need. We need to calculate the mean and the standard deviation. Well, luckily in this lesson, we've talked about some new notation. So if you look at the first entry on this, we can see that the first entry is X bar. So we've got the mean straight away. So we can write down the mean. Okay, so X bar, and we'll do this to 3 significant figures. So that's 5.607. So that's going to round to 5.61 to 3 significant figures. Okay, so that's the first thing from the calculator. And we also need to calculate the standard deviation. Now, standard deviation, we've got some notation for that also. If we scroll down, you notice that we've got sigma x is the second entry. Now that's the sum of all the data before you divide by n. So they've given us that. If you go down to sigma x, if you can see that, the little sigma, which I'm going to highlight. Let me, maybe I can make this a bit bigger. There we go. So I'll make it even bigger still. You can see this. No, maybe not. So I'm just going to highlight. So I've just opened the window up there. Sigma x, this value here, this is the standard deviation. Okay. Right. So x is in the data points, sigma as in the standard deviation. So we can now write that down. So you can write it as sigma with a little subscript x if you like. So that's going to be 2.94. 2, 3 significant figures. It might be a bit confusing with the subscripts. Don't worry too much. I mean, sigma n can be used for a data set as well. Sigma x to denote x as the data set. Don't worry too much about it. All right, let's see what else we've got just while we're here. So we've got those two. We've got some, if I just scroll down, we've got SX. We'll talk about that in a minute. We've got N, which is the number of data points. You've got the minimum value, and then we've got Q1, med, and Q3. Those are the quartiles, and med is the median. In other words, Q2, the middle quartile. Okay, and then if you just scroll down one more time, they give you the maximum value as well. So we've got quite a lot of information on that calculator. So that's really good. So it wasn't too hard, and we've managed to get the mean and the standard deviation really quickly. Okay, now what I'd like you guys to do is just to pause the video, and I'd like you to calculate the mean and the standard deviation using your ClassWiz or your ClassWiz emulator for KFC, and then we can compare results. All right, so now I've just put in the data for KFC from row 2. Now I've just managed to put a window on there from the calculator so we can see it a bit more clearly, although it is quite pixelated. So the numbers we're interested in are the mean, which is the top row, so that's sigma x up there, okay, and the standard deviation. Sorry, I meant x bar, apologies. The mean is x bar, and then the standard deviation, sigma x. Okay, so we can jot those down over here. And just make a note, that previous data was for McDonald's, wasn't it? Okay, so for McDonald's, we had this information. And for KFC, so we have an x bar, 4.29, so 3 significant figures. Okay, and the standard deviation of 3.15. Again, to 3 significant figures. These are in millions, of course. So there we go. So again, we can make some comparisons. Now you'll notice for the full population of data that we've collected here, if we compare the means for McDonald's and for KFC, McDonald's is doing better. Yeah. So there's no ambiguity there. And also, if we compare the standard deviations, we have more evidence now that McDonald's is actually performing better than KFC. It still has that lower standard deviation than KFC, which suggests it's more consistent in its sales and it's selling more chicken nuggets. All right, so next up, I'm just put a summary of what we've discovered in this lesson so far. So we found the sample means early on from that small set of data of 5 data points. We've got 4 in each case. That was inconclusive. Then we worked out the standard deviations, and then we found for each of those samples of 5. Then we got the idea that McDonald's performed slightly better based on the standard deviations. Then we took the population mean. Now, the population was from 3 weeks worth of data. The population mean definitely showed that McDonald's was doing much better. And Also, the standard deviation concurred with that because it was more consistent than KFC. So the more data we have, the better. And we've actually said that in this sentence just below here. So it tells you to notice that the means and standard deviations of the sample sets are not very accurate compared with the total population collected over 3 working weeks. Obviously, the more data you have, the better. Okay, so now comes the most important part. You may be familiar with standard deviation from your other subjects, and you may have thought already, hang on, this is not the formula we were given in our other subjects. It was different. We weren't dividing by n, we were dividing by n subtract 1. Okay, as you can see here. This is really important. Okay, I can't stress this enough. Okay, so you need to pay close attention to this. The reason why the formula is different is to do with whether you're working from a sample or from the whole population. Now, I've made the first sentence here bold. It says in core maths, we are more interested or mostly interested in calculating the standard deviation for a population based on a sample of data from the population. A sample. Now, when you're taking data that is based on a sample from a population, that means that we don't have access to all the data for the entire population. It might not be available. For example, a census is a sample of the population because not everybody will fill in the census form. So you have to make, you have to sort of judge it as an approximation. Now, what we can do is, because we know this is not the true standard deviation for the entire population, we apply something, and this is called Bessel's correction. Bessel was a mathematician, astronomer, he's a polymath essentially, and he came up with this slight adjustment to the standard deviation. Now, the way he corrected it, and I won't go into why he did this and why it's n subtract 1, is he just said if you divide by n subtract 1 rather than n, this will correct for the fact that your data is only a sample. Okay, so this is the formula we are going to be using, okay, from now on. All right, so make that look really important. I'm even going to put it in a red box because I think it is that important. Okay, so there we go. So there is a key difference. Okay, so when you're applying your step-by-step guide, if you want to use Bessel's correction, which you should be doing, step 1 to 5, when you're using the process that we described earlier in the tables, they're exactly the same. So no difference between step 1 to 5 in this and the previous method. What is different is step 6. The only thing you have to remember is that you're dividing by n subtract 1. Okay, not n. So that's just something you need to remember. Now, there is another problem, the ClassWiz. Okay, how does the ClassWiz deal with this correction? Well, it actually gives you the data, and I'm going to show you where the sample standard deviation in a second. Okay, so I've just brought up the results from the KFC data that we calculated a few moments ago. And I just want to draw your attention to something. So we've got various symbols here. We need to be able to interpret them. For the standard deviation, we've seen that that's sigma x, okay, which you can see situated here, okay, on the screen. But I've just made it slightly bigger. Okay, this is the standard deviation there, sigma x. Now, that's the standard deviation for the population. Okay, we want to calculate the SX, which is the sample standard deviation. Okay, now what we do to get that is, I'm just going to undo this. Okay, to get the sample standard deviation, we just simply click down on the display, and if you see the top number that's visible to you, Okay, this is SX. This is the number you want. Now, this is the calculation which takes into account the n subtract 1. Okay, so that's the number you're going to be using. Okay, I hope that's clear, everybody. Okay, so the last bit of this explanation, I've just added the corrected sample standard deviation. So this is applying Bessel's correction. You can see they're actually very similar to the population standard deviations that we calculated earlier. Okay, so those population standard deviations would cover the 3 weeks. But this correction allows you to make an estimate for what the entirety of the standard deviation might be. So the 3.05, I would just ask you to verify that. Okay, so if you put in the McDonald's data again on your calculator and just check that you agree with the 3.05. The 3.27, we came up with that earlier, which I showed you in the previous section. So I've just regurgitated that. But the McDonald's data, just check that you agree with the 3.05. So these are the SX values, okay? So the corrected values available on the ClassWiz, okay? And remember, if you're using the method by hand, where you're using the table, you need to divide by n subtract 1 to get that correction. So now we have a couple of worked examples to do. Now, what I would like you to do is just to pause the video now and have a go at the worked examples yourself, and then we can go through the solutions on the board and you can check you agree. You can also use your ClassWiz emulator or your ClassWiz calculator to check that your working is in fact correct. So please pause the video now. Okay, and let's have a look at the solutions. All right, so the first thing is we're going to calculate the mean of these data. So the mean, and remember we've got our new notation here, X bar. So X bar is the sum of all your X data, so capital sigma, and divide it by n. So we just need to add up all the data points. Well, if I just count them, we've got 1, 2, 3, 4, 5, 6. We've got 7 numbers, okay? So I know that my n is equal to 7. That's good news. And then when I add it all up, what do I get? Well, I'm going to have 6 plus 8 plus 12 plus 5 plus 7 plus 9 plus 13. And then we're going to divide all that by 7. So this is equal to 60 divided by 7, which is not a nice number. So we just have to work that out. Okay, so 60. That's a shift. There we go. Option 1, 60 divided by 7. Now it's going to give us a fraction. What's that? So it's about 8.57. So that's the mean. So it's not a nice number to 3 significant figures. Okay. Right. So we've got the mean. Now we can start filling in the table. Okay. So I'll fill in the table and then just check your answers with me. Okay. So I've filled in the table. I just want you to check that you agree with those numbers. And what we need to do next is we need to find the standard deviation. So the first thing to do is to find the variance. And we can do that because we've got the sum of the xi subtract x bar all squared. So that's no problem. So the variance, the sigma x squared, is just that number. So I'm not going to write out all the formula again. So it's just 53.7143 divided by n. Now, remember, we're going to use the Bessel correction here. So we do n subtract 1. So that's going to be divided by 7 subtract 1. Okay, so this is going to be 53.7143 divided by 6. Now we can use the calculator. So if I just put those numbers in, sorry, it's slightly obscured. In fact, I will just erase some of we've got the mean already. It's 8.57, so I'll just erase that so we can see the screen a bit more clearly. Okay, so let's put the numbers in. So we've got 53.7143. We'll divide that by 6. Okay, now this is the variance. So we'll write that in. So that's going to be 8.95. Okay, to 3 significant figures. Now, so therefore, the standard deviation sigma x is the square root of that answer. So on your ClassWiz, what you can do now is if you just select the square root function, okay, and just press the answer key, and just press the right hand arrow key just to come out of that, and then press equals, and then we've got 2.99. Okay, so let's write that in. So that's 2.99 to 3 significant figures. Now, because the mean was such an awkward number, if we check this on the calculator, we're expecting a tiny discrepancy because of the rounding issue. So next, we're just going to check this on the calculator, and we'll see if it works. All right, so I've just plugged everything into the calculator, the ClassWiz. So we're just going to check everything here. Notice that the first value x bar, we seem to have done that okay, 8.57. Okay, so we got that. Sigma x was 60, yes. Now, some numbers. Now, we applied Bessel's correction here to get the approximation for the sample population based on the sample. Now, you may notice this number here, s squared x, that's the square of that sample standard deviation, which is the sample variance, if you like. So that's why we've got the 8.95 here also. All right, so that's quite interesting. So we've got that. Now, just to get the final answer, which was the 2.99, I'm just going to scroll down, and we're just going to check this. Just erase. Just don't like that color. So let's see what we got. 2.99. Yes, there we go. So it looks pretty good. Even though it was rounded to 2 decimal places, we've got a good answer to 3 significant figures there. So everything looks good. Obviously, the table is there for you to appreciate how to do this by hand. But if you have the ClassWiz, it's much, much easier. And that's all expected of you, really. You don't have to do everything by hand. As long as you understand what you're doing and you understand how to put the numbers into the calculator, that's all we need. Okay, now for this second worked example, the final one, it's a good idea to just see how we can do this on the calculator exclusively, okay? We've got a few things to answer, and we've got to make some comparisons and draw some conclusions. So let's bring up the ClassWiz, and let's see if we can just reset this. Okay, go back to the menu. Okay, so remember it's option 6. We'll just plug in the numbers. It's one variable, and we'll plug the numbers in now. So we've got 32, 18, 23, 19, 43, 27, 35. Okay, I just have to move this a little bit. 26, 19, 23, okay, 21. All right, now we've put everything into the table now. So remember, now we press the option key, and then we select option 3, the one variable statistics. Now, it's a good idea to just read ahead when this situation comes up. We seem to have a few things we need to find out from this calculation. All right, so let's drag this over here again. So the first thing we need to jot down is the standard deviation for the group. So this is for group P. Okay, so I'll just make a note what we're doing. So this is for group P. So just write a summary for each one. Okay, so the standard deviation, Remember, we can use, we need to use the SX value for the standard deviation. So just scroll down, so that's 7.82. Okay. You'll notice as well, if you use the sigma x, of course, that's 7.45. So notice there's an allowance for greater spread in the wider population. All right. What else do we need? So we've got to make a comment about the standard deviation in part B. Then for part C, we're told to find the interquartile range. Okay, so we haven't done that so far in this lesson, the interquartile range. How do we find the interquartile range? Well, if you remember from GCSE and prior to GCSE, we just take the upper quartile, which we now call Q3, and we subtract the lower quartile. So we need to take the quartiles from this ClassWiz calculation. So let's do that. So the quartiles are not on the first sheet. Okay. In fact, let me just open that up. I'm going to see it a bit more clearly. So Q1 is 19. So let's make a note of that. Notice it doesn't actually give you the interquartile range, but it does give you the quartiles. And Q3 is 32. Okay, so simple subtraction, we can get the interquartile range. Okay, so therefore, interquartile range is just going to be 32, subtract the 19. Okay, so that's 32, subtract 19, so that's going to be 13. Okay, so we've got that. And then we're going to have to state a disadvantage. So we'll do that later. Now let's get the summary information for group Q now. So I'll put that in the calculator and then we can regroup in a second. All right, so it's option 6. I'm going to select option 6 and it's one variable again. So there's not as many numbers here. So we have 3, so 33 equals 24, 37, 66, 35, and 21. Okay, so that's all that. Then we press the OPTM button and select option 3. And once again, we've got everything we need. Isn't that wonderful? So for group Q now, all right, so for group Q, once again, we need the standard deviation. We'll use the SX standard deviation. So that's going to be 16. Okay, which is huge. Okay, and we also need the quartiles. So Q1 is 24. I'll just expand that window actually so you can see it more clearly. So yeah, Q1 is 24 and Q3 is 37. So once again, we just do a simple subtraction. So therefore the IQR is the difference between those two. So that's 37 subtract 24. That's going to equal 13. Okay. So that concludes all the calculations. So now we just have to draw some conclusions from this. So for part A, we've calculated the standard deviation for both the groups. If we can compare them, just out of interest, look at the massive difference here between the populations. And granted, we've got less information for group Q, which can be a handicap, as we'll see in a minute. So for part B, why is the standard deviation a better measure of the spread than the range in this case? Well, let's have a look at the data in a bit more detail. So I'm drawn to this number here, 43. Compared to the rest of the numbers, This is what I would call an extreme. Well, it's not extreme. It could be an outlier. We don't actually know as yet. You need to do further calculation. But if you're calculating the range, remember the range takes the biggest value and the smallest value and finds the difference. So for part B, the problem with the range is, of course, the range is affected by extreme values. So we'd have to write that down. So that's the main disadvantage. Yes, it's easy to calculate, but if you have really large values and really small values, but the rest of the values are all kind of close together, the range won't pick that up. Okay, so the range is affected by extreme values. That's a problem. Okay, and we have an extreme value with the 43 minutes in group P. Okay, so that apprentice took a lot longer than everybody else to complete the task. So that's one disadvantage. The interquartile range, we've done that for both. It's the same number for both, 13. So we've done that for C. For part D, this is the final thing, give one disadvantage of using the interquartile range to measure the spread in this case. Well, the interquartile range is better than the range because you're using the quartiles, it's unaffected or less affected by the extreme values. Okay, so that's good. But the interquartile range, it doesn't use all the data. Okay, that's another thing to bear in mind. The standard deviation, of course, uses all the data, and the only real disadvantage of the standard deviation would be that it's actually quite complicated to work out. But in this instance, there is a key factor which makes the interquartile range quite disadvantageous. And the problem is the fact that the first data set has far more values than the second data set. Okay, the second data set's interquartile range will be much less accurate than the data set for group P. So that's the problem. So we'll write that down and then we'll draw this lesson to a conclusion. So the problem is that in fact, I'll start that sentence again. So for part D, group Q has fewer values or data points than group P. Okay, and when that happens, the interquartile range may not give a fair comparison. Okay. Yeah. All right. So that's one interpretation. We'll go into a bit more about interpreting the data later on in the course. Okay. But you've had a really good overview of where the standard deviation comes from, how to apply it, and there's some exercises for you to now try. Okay. Thank you very much.